Now to measure then the speed of light, took actually quite a while to do. We're just going to look at the kind of final basically experiment to do that. That was done by Albert Michelson in 1905. But certainly before him, there's quite a few attempts then to accurately figure out how fast the light was going. But this is the one that we, or the value then that we still use today. So the experiment then that he did at the beginning of the last century there. And so what he did then is he had this rotating mirror array. So again, a couple of problems with measuring the speed of light. Because it goes so fast, you either have to use very long distances or have a timing device that's very, very accurate. So he used kind of a bit of both with these ones here. So he had this 8-sided mirror array, and this basically would spin around, and that became more or less his timing device. Now he did this basically from kind of one mountaintop to the other. I think this was in Washington State. But this was 35 kilometers, and so the light was traveling basically 35 kilometers to this mirror and then back again. Now you will notice that there is a small angle here, but that it really isn't that relevant. This mirror relative to this length, again, was very, very small. And so these angles, this has been blown up a lot on this diagram, but this was a relatively small mirror array and a very long distance here. So these are going to be more or less treated as straight lines there. You can certainly do the trigonometry to kind of figure out the angles there, but they're quite slight. And so we'll just treat those as basically a straight line there. So this is just much, much bigger than it actually was. So what you want to look at this, and we'll look at this kind of in 2 points here. So first of all, if I have this mirror array here, and these are all symmetrically aligned mirrors, what you can do is if this mirror is not moving at all, you can direct a beam of light. It's going to hit this side of the mirror. Now that'll cause it to bounce over to here. Then it will reflect back, and then it'll hit this mirror, and it'll go basically lined up to this telescope there. And so you're going to have it running along there. Now that's with the mirror stationary, and if these two are at the same angle, again, so you have to put a bit of time into building this mirror array, then this will be directed straight across here. So then what you're going to do is you're going to start rotating this mirror around. And so you're going to keep this light pointing over here, and you're going to speed up this mirror until basically you can see that light again. Because what's going to happen is you want this to basically rotate in such a way as that this only goes 1/8 of a rotation in the time it takes the light to get to this curved mirror and back. So again, if this mirror is not moving, it hits this mirror, it bounces back, and this mirror is in just the right position basically to direct the light right at this telescope. Now, if this mirror, though, is rotating, and it rotates 1/8 of a rotation in the time it takes the light to get from here to here, this mirror down here then will have rotated to be in this position. And so if you do it just right, that next mirror will be in the position then to redirect this light. Now, if this is going a little bit too fast or a little bit too slow, then that light will either be moving up or down, and it won't be lined up with this telescope. Now, the other thing to keep in mind is, again, if you speed it up beyond there, if you do 2/8 of a rotation, 3/8 of a rotation, 4/8 of a rotation, you'll have the same issue there. And so what you do is you basically line it up when it's stationary and then get this rotating, and then basically the slowest rotation that still allows you to see this light then is going to be your timing device. And so then you can use that frequency of rotation basically to get the time it took for the light to go from here and back again. All right, so I just want to run through a couple of examples for how we can solve then for a given speed then using that Michelson experiment then for the speed of light. Now, a couple of things to watch. Just watch how many sides your mirror array has. He did it with an 8-sided one, but your questions will maybe change that up a little bit. Also watch the distance that that fixed mirror away. This is always going to be related then to the distance that the light travels, but don't forget you have to double this. And so the light then goes from that rotating mirror array to the fixed mirror and then back again. So this 30 kilometers, and it will always be just given one way, you have to remember that the light is traveling both ways. And so that'll be your distance. In this case, that'll be 60 kilometers. Now the rotation then is going to be always related to your time. And so this one then is rotating at 813 rotations per second. And that's just going to be in hertz. And so that will be a frequency. And so this will be probably the one we'll spend the most time on as we're going through these. And we just need to take that into our time measurement there. And so what we're looking for here is the speed of the light. And so we are looking then, of course, for the speed or the velocity then in this particular question. So we'll start with then that time then device here, so that 813. And so what we're looking for is then the time for one rotation. We'll start there. Okay, and so this is moving at 813 rotations per second. And so what I'm actually looking for then is a period. So this is rotations per second, so that's a frequency. So I'm going to take a period of 1 over that frequency. So I'll get 1 over 813. Now it's in 1 over second, and so then that just becomes seconds. And so then I'll get, for one full rotation, 0.00123 seconds. Okay, that's the time for one full rotation. Now the other thing that you need to watch for then is that we don't actually need one full rotation. We just need basically 1/6 of that rotation. So however many mirrors sides you have for that mirror array, that's basically the fraction of the one rotation that you need. So it does a full rotation in this time here, but we're looking for what's required then for it to line up with is just 1/6 of that rotation. And so then my time for 1/6 of rotation is just 1/6 times that. And if you had more or less than sides to your mirror, you just change your fraction then accordingly. And so I'll have 1/6 of this time over here. And we're just dealing in seconds. And you want to be dealing with seconds for these ones here, so then we can get meters per second then for our overall speed. And so I get 2.05 times 10 to the negative 4. And you should get relatively small values then for these ones. And so this is the time then for 1/6 of a rotation. And in the time that that mirror array did 1/6 of a rotation, our light traveled 30 kilometers one way and then 30 back. So that's going to be 60 kilometers, and make sure then that you're just changing that to meters. So it's moving at a constant speed, so I can just use my d over t for my velocity. Don't forget to change again that to meters. So 60,000, so 30 kilometers in each way, so it'll be in meters. And then my time is then that 2.05 times 10 to the negative 4, and that'll be in seconds. And then when I multiply that out, divide that out, I'll get 2.93 times 10 to the 8 meters per second. Now you will find for these ones here, where it's giving you experimental data, it typically will be very close to that 3 times 10 to the 8, but not quite exactly, just so we can see that you're actually doing the calculation to get there. Now for this one here, we're looking for the minimum frequency of rotation. So now we're looking at the rotating mirror array for this one here. Again, always watch for how many sides. So this is going back to that standard 8-sided mirror there, but that can certainly change from one to the other. Now in this one here, we are looking at 30 kilometers apart again. He was 35, both of these were 30. But certainly any distance there is possible. Just remember that you're always doubling that distance there. Now for this one here, we don't know what the speed of light is, and so we're just going to use the theoretical value for this one here. And so if you're looking for something other than the speed, then you can just use then the theoretical value for the speed of light. Now the frequency of rotation is always related to time. So what we're going to do is we're going to first start by finding out how long does it take the light to move this 30 kilometers. And since we're not looking for velocity here, we're going to use then the theoretical velocity for the speed of light going through air. So we can just go distance divided by velocity. Again, 60,000, so don't forget it goes there and back again. And we want to change that to meters, so make sure that you're just being careful for that. And then we have the 3.00 times 10 to the 8. If we're not looking for the speed, we'll just use the theoretical speed then for those ones. And so we get 2.0 times 10 to the negative 4 seconds for our time. Now remember, that time is not a full rotation, that's 1/8 of a rotation. And so 1/8 of a rotation Now when you're solving these, you don't need to write this one out, but just so we are clear about what we've solved for here. Again, the light travels to the fixed mirror and back again, that's 60,000 meters in this amount of time. And in that time, we just do 1/8 then of a rotation. And so we're always looking for that smallest variable possible there, or that smallest fraction of rotation possible. And so however sides you have, it's going to be one, obviously, of that number of sides there. So in this case, 1/8. So if 1/8 of a rotation takes 2 times 10 to the negative 4, then 8 times that will be one full rotation. And so just simply multiplying that value by 8, And I'll get 0.0016 and then seconds for that one. So that's the time for one full rotation. Now if I was looking for a period, then that's where I would leave it, but I'm looking for frequency, and frequency then is 1 over that period, and so I just take the reciprocal of that, and that'll give me then my frequency of 625 hertz. And what you'll notice for these ones as well, the more sides you have on your mirror, the slower that frequency needs to be. The fewer sides, the higher that's going to go, so the faster you have to spin those mirrors. Also your distance here, if you set this distance further, you can have a slower frequency. The closer that distance is as well, again, the higher the frequency then needs to be. But always remember for these, your rotating mirror array, that's always your time. And again, don't forget, you're just looking for then always, the time is always a fraction then of the number of sides then you have for that mirror array.